Good morning. Welcome to episode number 14 of the Zoomtown experiment. Today's experiment is going to be all about another time-of-flight sensor that we're going to use for collision avoidance. This is what we're going to cover today. We're going to review the purpose and function for this sensor, review why the VL53L0X failed to perform to our standards. We'll review the performance of the TCRT5000 sensor. We're going to review this sensor, the GP2Y0E03 time-of-flight sensor made by Sharp. We're going to do a practical setup for testing. I'll be showing you a schematic. In this case, it'll actually be a Fritzing diagram, very simple one. We'll take a look at the code, and of course we will be reviewing the data sheet as well. Then we're going to perform some practical testing just like I did with the other sensors for this purpose. And finally, there will be an analysis of the sensor denoting whether it's a good fit or a bad fit for our application. Let's begin by taking a look at this sensor. This is it here. It's very small, definitely will fit in within our requirements for size and space. It comes with a flying lead, which is wonderful. The price is $3.60. Is that good or bad? It depends. If it does the job, it's a good price. Normally when I review the data sheet, I want to highlight some of the specifications. For some reason, it's just not working today. But here's what it is. This is the sensor. They call it a distance measuring sensor unit. And it is kind of a little unit or module because it has all the components necessary for the sensor to communicate with a microcontroller. Its measuring distance is 4 to 50 centimeters. 4 centimeters would be about 1.5 inches. 50 takes you way out past our needs of 12 to 15 inches. So the range on it's very good. It has two different interfaces, digital communications through I2C, and it has an analog output type. It's using an infrared LED. Its applications include cleaning robots, human-type robots. That's rather fascinating. Touchless switch, sensors for energy saving, automatic turn on and turn off things, and amusement equipment such as robots, game machines, etc. Low voltage operation will operate down to 2.7. So that's a real good thing there. The interface is a total of 7 pins. The ones that we're concerned with starting out will be our input voltage, analog voltage out, ground, SCL, and SDA for the I2C interface. And that's again denoted here. What I want to show you here is our supply voltage. They're saying negative 0.3 to 5.5. We're going to, that's absolute maximum. This is our supply voltage that we're concerned with, 2.7 to 5.5. And with our Zoomi, we will have several resources for 3.3 voltage. And that'll be important here in a minute. Average supply current is typically 26 milliamps. That's not really unrealistic at all. It's pretty good, actually, for an infrared LED of this type. This is an interesting graph here. It's showing distance data through I2C, distance to the object. Notice they're saying a reflective object. They're denoting that. And these would be the values from I2C to the distance down below, and then your voltage out from its analog output for the sensor. Well, I can't find the spec that I was thinking of, so hopefully I didn't imagine it. But what it was relating to is that you had to have enough current supply to take advantage or to cover the pulses of light, because it can peak out at about 100 milliamps very, very briefly. And so when I powered this in one of the tests off of the PICO, it wasn't behaving very good. So then I added an external power supply directly to the device, and it seemed to behave better. If I find that again, I'll put a note at the end of the video or in the comments down below, or rather the description. But the other thing that is important is to understand that we've got a fan out of approximately 6 degrees for the sensor for transmission of the beam and capture of it on the bounce back. What they're saying here is at 50 centimeters, roughly 20 inches, you have to have an object at least 9 centimeters or 3.5 inches in order to get a good reading. In our case, we're going to be using one of my new prototype bodies for the Zoomi as our test subject. We'll also use a couple other devices as well to get our test readings. But at this point, we're at about 2.5 inches, so we're not going to get accurate readings out at 20 inches, but my concern is in that 1 to 12 inch range, and we should be good with that. We'll take a quick look at the Fritzing wiring diagram. Here's our PICO. We are connected on our analog number 2. That would connect to the modules V out A for voltage out analog. And I'm sharing a common ground between our external power supply and the connection to the module for ground and VCC. Is this shared ground necessary? On my bench it is, but in the Zoomi it's not important because everything that's on there is powered from a single voltage source, the 18650 cells. Now we'll take a look at the code for this, and I need to explain a little bit more along with that because this is my second version of the software. I initially intended to do this with I2C, and I downloaded several different MicroPython libraries to do this with. Unfortunately, I couldn't get any of them to work correctly or properly without errors and problems. So I just simply abandoned that and then went to the analog output capability of the sensor, and I'm reading that on our analog to digital channel number 2. And that provided to be much better functionality, and it seems to be giving fairly consistent results, at least consistent enough for our needs. I shouldn't say consistent, accurate enough response data for what we need to do. That'll make more sense once we start looking at the plotted data. But our program is very simple because we are using analog. We just got a little function here that's going to take the analog reading and working from some basic practical test data where I can convert the sample reading coming from the sensor and apply how many of those units per inch for converting from the sensor reading to inches. And that's what this is all going to do on this line here. Going to take the voltage max at 45,000 from our ADC channel reading minus our sample divided by the value divided by the value for inch is divided into that. And then an offset value here because sometimes the sensor is going to be not necessarily right at the front edge of what we're measuring. So we might need a little offset to get our 0 point in line with 0. And we'll round that to 2 decimal places. That's all we need. And then we return that value. And because we're still kind of starting up the ADC, I delayed. Actually, I'm going to change that to a full second. Usually analogs take a few seconds to get up to speed, we'll call it, and function properly. From there, we jump right into a simple loop. We're going to also track how long it takes to make these measurements. So we will record the start time. We'll get our sample reading from the sensor. We'll convert that to our distance. Then we're going to record the end time, and then the run time is calculated from this function in time, which is the ticks difference, and that is a value in microseconds. And then we're going to print that out along with the run time that it took to get each of the readings. And we'll sleep for 100 milliseconds between readings just so that I can kind of read the data down below. Now we'll just start out running it right now. And I'm going to put my Zoomi at about 4 inches. And we'll make the bottom here come up a little bit. And as you can see, we're right around 4 inches. So it's calibrated so-so. I'm not going really crazy with it at this time for calibration because I'm not sure of the surface that'll be on the Zoomi. It may be more glossy. It may be dull. It may be, instead of blue, it may be white. We don't know a lot of details yet. I'm just trying to get some relative information from which I can make a decision if this sensor is going to work for us. Now what I want to do is, let me stop this. What I really want to do is to log the data like we did for other sensors. If you've watched the previous episodes, especially the one where we covered the VL53L0X time-of-flight sensor, the problem with that particular unit was it took an incredibly long period of time to take a measurement. Now, yes, it was only milliseconds, but a lot of them for our perspective. So that was one of the drawbacks to that sensor, as well as its high price, and its accuracy was, frankly, pretty good for what it was. Then we moved on to the TCRT 5000 photoreflective sensor, the same sensor I'm using for line following. Now that had another problem, and it worked pretty reliably and pretty consistently, but it's easier for me to show you on the graph the thing that worries me the most. If we look at our scale here along the bottom, this is 10 inches. These are the values coming from the sensor, so that would be the value I would use to make a decision from. Now from 10 inches all the way to 4 inches, this is almost a flat line, so the sensor can't differentiate any distance in there. Down to 3 inches, it only drops down a little bit, and I don't know if that's really reliable enough. Now here's where it gets into the tough decision. At 3 inches to 0 is really right now my warning zone. I got to do something within that time and distance to prevent a collision. Now, if we hop up these cars and we start going faster, I'm going to definitely need more than 3 inches to make that determination. So I'm really nervous about that. I think that 3-inch limitation is really killing me for future capability of our Zoomi. You'll also notice it's not very linear at all. It falls on this kind of crazy curve. So making a good decision, or perhaps if I have 2 decisions I make, where at one value it might be slow down, the next value is full stop, trying to reason that out without linearity is going to be a little tricky. So that is part of what led me to this sharp sensor. Now, you're going to kind of like what you see on this next graph. Just kind of keep that little image in mind over our starting distance to our ending distance. So from here to here. Now this is against our white box. Notice out here would be our 12 inches down here would be about our 1 and 1.6 inches, the absolute minimum value it would function at. And notice the nice straight lines between light on and light off, almost no deviation. And with the very crude calibration I've done, notice how close the actual, what the location was or the distance should have been, and the actual readings. Extremely parallel all the way down with a little bit of hockey stick movement here where we're into that last little bit before we're at too close of a distance for the sensor to operate. Now that white box is pretty ideal. It's got a nice large flat surface on it, bigger than our Zoomi body. So we went on to the white Zoomi. Now here you'll see that we fell off a little bit where our distance measurements from about here to here got a little out of linearity. They started drifting upwards. And I suspect that is because if you look at the Zoomi body, we've got our width here, which is, let me get an accurate measurement on it. We'll say about 2.5 inches, but it's also curved. So we're going to, as the sensor fans out with its beam, we're going to lose precision based on this alone, the curvature and the narrow width. But is that really a problem? Not so much. At this point, I'm all the way out to here, which will be about 7 or 8 inches, at which I can make a determination of what to do. So I've got even more than twice the distance to make these decisions. And even beyond that, it's still fairly accurate information for what we're trying to achieve. Now, let's look at the blue Zoomi. Again, we did the light on, light off testing. Are still got a little hockey stick stuff going on here, but from here on out, it's fairly linear again. And again, it's got that same drifting, and I presume that is specific to the curvature of the Zoomi body. Whether or not I even need to worry about that, it is something I could correct in the body design if I needed to. I could make that back surface flat, because most likely we'll be bumping into the back of another Zoomi. But at this point, truthfully, I'm not too concerned, and I'm really happy with these readings. Not a lot of bad data in there, especially when I'm comparing to my next best opportunity. My next best choice was this one. From that to this, it's worth 3 times the price to me. So let's put this through the analysis and show you what my decision-making process is looking like. To start out with, it's giving us moderately accurate readings. Again, I'm not overly concerned about absolute precision on this. I'm looking more for an about situation. Anything within 1/4 or 1/2 inch is probably going to be perfectly fine for our application. At $3.60 each, it seems expensive, but the capability justifies it, I hope. I'm going to put that caveat on here because I have done another sensor in the past, and it was a Sharp, I believe it was a Sharp brand distance sensor, where I had a larger robot with 2 of them on the front of it. And I seemed to get conflicting readings because 2 sensors were being used in the same vicinity of each other, per se. That one, I don't remember the specs, and I don't even remember the model number of it. But this one with a fairly small cone shape of the fanning of the sensor, I think this is going to behave better, but it could bite me in the butt in a few months here. It's easy to use and code, nothing like analog readings. It's efficient to use, power and time. The current draw is very minimal, and the amount of time to read is very minimal. At 160 microseconds, or 0.16 milliseconds, I really can't complain about that. It's compact. It's very easy to wire up because they include the connector with the flying leads. Cannot use power from the PICO, but that's truly not a concern because we have an external or a separate 3.3 volt power supply on the Zoomi. We're getting very linear readings from 2 to 12 inches. Granted, the far end floats a little bit, but it's certainly not unrealistic for our application. All around, at the moment, I'm going to say we're going to pass this along and we're going to put it into the Zoomi. Unless I learn something different, right now we've got a plan to move forward. So that'll wrap it up for this video. Thanks again for watching, and I look forward to seeing you next week.